Hello and welcome back to the Reigate Maths series on the Travelling Salesman Problem for the second year of the Decision 1 unit for the A-Level Further Maths. My name's Simon, and in this video we're looking at the second of the two methods to find an upper bound to the Travelling Salesman Problem using something called the Nearest Neighbour Algorithm. If you haven't yet gone to have a watch of the video on the minimum spanning tree method, I advise you do that first to get an idea of what the other method is. So the nearest neighbour algorithm is generally a little bit quicker than the minimum spanning tree method that we looked at in the previous video. The problem with the nearest neighbour algorithm is it looks a lot like prims in terms of the way we approach it. So what we're going to look to do is the nearest neighbour algorithm finds a tor. So what we do is we start at a vertex. Usually we'll be given that. For this first example, we're going to start at A. What you will then do is you will look at A and go, okay, what is the closest vertex to A that we haven't already chosen? Well, that's B. And I'm going to write that down. Well, then we look and go, okay, what's the closest vertex to B? Well, it's A, but we've already chosen that. So we're going to choose C, which is the next closest. We then look at C, and we pick the closest to C that hasn't already been chosen, which we can see is E, which is 200. We then keep going. The closest to E that hasn't been chosen is H with 131. And then F with 70. We've not got many more to choose. We've either got D or G, so we're on F. D is 220, G is 144. And then we have to go to D. 155. The thing with the nearest neighbour algorithm is you've got to then remember to go back to the start. Regardless of how long it takes you, A to D or D to A is 382. So although you might be able to spot shorter routes to get from D to A, you can't use that. You have to go straight from D to A. And this is the nearest neighbour tor starting at A. We total it and we get 1,250 miles. So what I would like you to do now, using the same method, is pause the video and have a go finding the nearest neighbour tors starting at B and C. So starting at B, we go B to A, which is again the 47. Then we go to C, 84, and then it's broadly the same. E, which is 200, 131 for H, 70 for F, 144 for G, and 155 for D. The thing with this is you've then got to remember to go back to B, not to A, for 402, which gives us a total of 1,233 miles. Using a similar method for C, we get an upper bound of 1,242 miles. So although this second part of each of the tors is the same, the orientation of this first part really matters. And we might then get different answers if we use D, E, and so on. Now, the thing with the nearest neighbour is really it will only ever give you n possible tors, one for each vertex. Technically it's 2n because you can go backwards as well, but that gives us the same length, so we don't really count it. So the nearest neighbour algorithm is really good, really quick, but it is very limited in what it can do, whereas the minimum spanning tree method is a little bit more varied. Now, from the method we looked at in the previous video and this method here, we've now generated 4 upper bounds. We've got 1,254, 1,250, 1,233, and 1,242. So our best upper bound is the smallest, which is this 1,233 miles. Start this from nearest neighbour starting at B. That is not necessarily the optimal solution to this travelling salesman problem. It might be, but we don't really know, not easily. But it is a good solution. And that's what nearest neighbour finds. And that's generally what these upper bound algorithms find, is they find good solutions, even if they're not necessarily the best ones. Now, nearest neighbour is pretty quick. You can do it on a matrix, like you do with prims, with labeling columns and crossing things out. But just to kind of highlight things you need to be careful of. Nearest neighbour, we're always looking at the previous or the most recent vertex we're going on. If we use prim's algorithm to find a minimum spanning tree, you are looking at all of the ones you've chosen so far. So that's the first major difference between the nearest neighbour and prims. Don't get them mixed up. The other big difference, and this is usually not the issue that students find, is for nearest neighbour you go back to the end, prims you don't. Okay? Sorry, you go back to the start. So once you've finished, prims you stop, nearest neighbour you go back to where you started. So this is our tour. This is if we don't have the A on the end, this is a spanning tree, but it's not necessarily the minimum spanning tree because we've used nearest neighbour, not prims. So be very, very careful not to get them mixed up. But otherwise, this is the nearest neighbour algorithm. It's very quick, but it can only find as many tours as there are vertices. In the next video, what we're going to look at is the method to find a lower bound. There is only one method for that. And then we'll also look at how we can combine the two solutions to state the set of values in which our optimal tour could be. Thank you for watching.